Alright guys, so in this video we're going to look at the first problem from the worksheet that I gave you in class. Basically this is looking at forces acting on an object that's in equilibrium. Okay, in this case it's a crate that's at rest on a horizontal floor. We know it's equilibrium because its velocity is not changing. Okay, it's at rest, it's staying at rest, therefore all the forces have to be balanced. It can't be unbalanced because an unbalanced force would cause a change in velocity. Now, what I'm going to do is I'm going to talk through the process as it is on your worksheet. Okay, what I would like for you to do is at particular times I'm going to ask you to pause it and work it out on your own. And so I would like for you to actually do that. That's the value of this activity, is that you can actually try it out and then you get immediate feedback, and I'll kind of talk through the process and how we do it. Okay, if you just sit and watch through it, then it's just like a normal lecture and you're not really getting that much out of it any more than any other normal lecture. So go ahead, do what I ask and pause it and work through, and then continue to do that throughout the rest of the worksheet. I'll have two other videos that work through two similar problems. The big idea here, of course, is that we're looking at problems that deal with Newton's laws, that deal with the math associated with the balancing of forces and things like that. I don't want you to see these as individual types of problems. It's all one type of problem, a Newton's law problem. So let's consider the first one. A 35-kilogram crate rests on a horizontal floor, and a 65-kilogram person is standing on the crate. Okay, now eventually you'll notice if you look through A, B, C, D, E, you'll see that eventually the point of this is that we're trying to solve for the normal force. Okay, but rather than go pull an equation out of your hat that applies to the process, what we want to do is we want to be able to think about this process and put everything together so that we can work any type of problem like this, okay? Any Newton's law problem. So let's do part A. Draw a force diagram showing all of the forces acting on the crate. Please pause it and do this on your own. Alright, hopefully you paused it, you did it, you're back. So let's draw the force diagram. Here's my crate. Alright, so as we think about the forces acting on the crate, we've got non-contact forces and contact forces. The non-contact forces, the only one that we've dealt with so far is gravity. So is gravity acting on the crate? Why, yes it is. So that's the force of gravity, or how hard gravity itself is pulling on the crate. Okay, now we look at contact forces. Okay, so contact forces are tension, if there's a cable or rope, which in this case there isn't. Friction, if the object is sliding or trying to slide. In this case it's just sitting there, so no, it's not trying to slide. And third of all, normal forces. Now normal forces are anything else that's contacting the crate. So what are the things that are touching the crate? Well, the person is standing on top. Okay, if the person is on top, that means that he is pushing down on the box. So let's draw the force of the person pushing down on the box. So this is the force of the man. Okay, now I've drawn it bigger because his mass is bigger than the mass of the box, so his force is going to be greater than the force of gravity. Now, in the end, we also need, obviously the crate is sitting on the floor, so that means it's going to be pushing, the floor is going to be pushing up. Okay, now this normal force obviously has to be equal approximately to the sum of the other two forces. Okay, so there's our force diagram. There's no other forces acting on it, and therefore we're done. Question B, are the horizontal forces in equilibrium? Are they balanced? How do you know? Please pause it and work through this question. Alright, so we look at it and we say, yes, the horizontal forces are in equilibrium because there's no horizontal forces. There's nothing unbalanced. So no unbalanced horizontal forces. Okay, we can also say that as we know that its velocity horizontally is not changing, right? It's not moving side to side or speeding up or changing direction. And so there's no horizontal change in velocity or acceleration. Okay? Try letter C now. I'll give you pause it and do letter C. Alright, so hopefully you're back. Vertical forces in equilibrium. The answer again is yes. How do we know? Well, the box is just sitting at rest. Newton's first law says that if the forces are balanced, if it's in equilibrium, then it will maintain its state of motion. If it stays at rest, the forces are balanced. So again, no vertical change in velocity. All right? Awesome. Let's go on to D. D says write an equation using only symbols for the vertical forces acting on the object. Remember to use trig if it's necessary, and then use the plus or minus, right? Positives and negatives. Positive for up, negative for down. Please pause the video and work this question out. All right, so vertical forces. Hopefully you wrote that the sum of the vertical forces is the normal force, which is going up, minus the force of gravity, because that's going down, minus the force of the man, which is pushing down. All right, and those are the only forces acting on the object vertically. We've got the plus or minus. They're all directly vertical, which means that there's no angle, and so we don't need the trig. So there's our answer. Let's go on to part E. Insert numbers and solve for the normal force that the floor exerts on the crate. Please try to do this on your own. Pause. All right. Now, in the one above, we should have actually written that these all add up to give you 0, right? Because we already said that it is in equilibrium. That means when you add everything together, then it adds up to 0. So let's go ahead and put some numbers in. Okay? We're looking for the normal force, so we know that that's going to be our unknown. The force of gravity on the object we know is going to be 35 times negative 9.81. So let's go normal force minus 35 times 9.81, okay, minus the force of the man. Now some of you realize that the man is pushing down because gravity's pulling down on him. Now in this case we can actually say that the force of the man on the box is equal to the force of gravity on the man, because if we consider the man, right, if I draw a force diagram on the man, there are two forces acting on the man. You've got the force of gravity, and you've got the normal force of the box. And so since those are the only two forces acting on the man, then we can easily say that the force of gravity is equal to the normal force. So that means that we can say minus 65 times 9.81. Okay, and obviously all of this is equal to 0. Keep in mind that the force of gravity here, and when we drew it here, that's referring just to the force of gravity on the box. Okay, the force of gravity on the man is on a different object, so we wouldn't consider that as part of our force diagram. We don't consider that as part of our equation. We only need the forces that are acting on the box. So from this point it should be fairly easy. Multiply 35 times 9.81, multiply 65 times 9.81. Add both of those to the other side, and you should be able to get the answer. So let's go ahead and pull up our calculator. We've got 35 times 9.81, so minus 343.35, minus 65 times 9.81, so 637.65, and easy math to solve. Move them to the other side, so we've got 343.35 plus 637.65, and we get 981 newtons. So the normal force in this case is 981 newtons. There you go. First problem's all done. All right, go on to the second video and try the next one.